This is Calculus, Topic 4, Homework Problems 15 and 19. 15. For a rectangle with a perimeter of 36 to have the largest area, what dimensions should it have? Well, since we're looking for largest area, we need an area formula for a rectangle. A rectangle, the area is L times W, or length times width. So to find the largest area, eventually we need to take a derivative of this. And the problem with taking a derivative of this, we have two variables. This needs to be one variable, then we can take a derivative. So let's write down the rectangle. Here's a rectangle, and there's a length and there's a width. And we're told that the perimeter is 36. That means from here to here, then to here, then to here, then to back to here, all of that is 36. So from here to here to here to here, that's 2 L's and 2 W's. So 2 L's and 2 W's will be a length of 36. Now I can use this fact right here to make a substitution in order to get an L or W. So I'm going to solve for W here. So this will be 2W equals 36 minus 2L. I put the 2L on the other side as a negative 2L. Then I'll divide everything by 2. And I'll get W equals 18 minus L. So now I have a substitution for my W. So this is now A equals L times 18 minus L. And this gives me 18L minus L squared. Now A is a function of L, and I will take a derivative of it now. So this will be 18 minus 2L. Now, in order for the derivative to give you max or min, you set the derivative equal to 0 and you solve for the variable. So if I put the negative 18 on the side, I'll get negative 2L equals negative 18. Then divide everything by negative 2. I get L is positive 9. So this is the length. Now for the width will equal 18 minus the length, which is 9 again, and W equals 9. So the dimensions for this will be 9 by 9 for length and width. Okay, the area of a circular sunspot is growing at a rate of 600 kilometers square per second. And we want to know how fast is the radius growing at the instant it equals 10,000 kilometers. Well, the picture of that is this. You have a circular sunspot. Here's what it looks like right there. And it's growing. Well, so it's going from this size to this next size out here. And it's growing at a rate of 600 kilometers square per second. Let me talk about a kilometer square. A kilometer square looks like that. Okay, it's a square. So we're getting 600 of those every single second into that little one, and that's why it's becoming this size out here. Okay, so that's the rate. You're getting 600 of these little squares every second. That takes you from this small size to the next larger size. Okay, so let's write that down. That's 600 kilometers square per second. Now let's represent this as a rate. Okay, because it is a rate, so we're going to need a derivative. So kilometer squared, that's a change in the area, because these little guys, that's the area. So it's a change in the area, and the S is measuring the change in the time, seconds. This is seconds, so change in time. So where this comes from is from knowing what the units stand for. This stands for area, this stands for time, so change in time for change in area. Now, what are we looking for? How fast is the radius going? Well, the radius originally went from the middle here to the outside, but as this thing got bigger and bigger, the radius started traveling on the edge to this spot. So that means the radius is actually moving at some type of kilometers every second. Now there are different speeds, because when the radius got to here, it was traveling much faster than when it got to this spot right here as this circle got bigger. So there's all kind of speeds. The one speed that we want is the speed of when the radius has finally gotten to 1,000 kilometers. So what is the speed at the point 1,000 kilometers. Okay, so in order to get that, let's start off with the area formula for this circle. Area equals pi times the radius squared. And I'm going to take a derivative of this with respect to t. And how I know I want to take with respect to t is this right here. Oh, one more thing I want to do before I take a derivative of this. Since what I'm looking for is the change of the radius per second, that's going to be a dr, that's radius, change of radius, per change of time. That'll give me the how fast the radius is growing. So don't know the number yet, but that's going to be in kilometers. The radius is going to be a kilometer, and the time is going to be measured in seconds. All right, so again, and you see the dt on the bottom, which means that that's your derivative with respect to t. So the derivative of a is 1. But using chain rule, we also get dA over dt. Okay, because a is being treated as a function rather than a variable. T is the actual variable. And again, since t is the actual variable, r will be treated as a function. So again, we need chain rule. So this will be pi, and then this will be 2 times r for the derivative, but chain rule gives us dr over dt. So here we have the change in radius per change in time. Here we have change of area per change in time. And we know this one right here. We know the change of area per change in time is 600. So 1 times 600 pi, and 2. Now what's the current radius? 10,000. And we're looking for the dr, the change in radius per change in time. Okay, so I'm going to divide all this by pi, 2, and that 10,000. Other side also by pi, 2, and the 10,000. Okay, here we go. Let's clear that. And what we have here is 600, yeah. 600 divided by open parentheses, second function pi times 2 times 10,000. Okay, got that. And, ooh, small number. So this will be 0.0095. And I think it says I need to answer in 3 places. So I need to go to about this spot right here. So that needs to be 0.010. Okay, that's 3 places. And that's in kilometers per second. And that's the speed that the radius is traveling at that spot right there.